deflection lift, as we've talked about it, is predicated on pretty much the second of Newton's law that we talked about, and that is the equal and opposite reaction. And what it amounts to is, if I have, we talked about bouncing the ball. If you bounced a ball, then the ball exerted a force on the floor, and the floor exerted a force back, and that caused a change in direction. If we now relate that to air particles, and what happens is, if you look at an air particle and in a wing, and it doesn't matter whether we actually have the wing moving or we have the wing sitting still and the air moving, the result is going to be the same. And that's why we can do this with a wind tunnel, is we hold the wing stationary and blow the air by it at a certain speed, and we can test the results. And it's because it's relative motion, it doesn't matter. So you have an air particle here, and it's sitting still originally. And if it's sitting still, in order to make it move, I've got to apply a force to it. And since it was sitting still, the force applied is actually going to give me the velocity that we need for it to go by. I'm going to apply that force with an airfoil. And so if we look at it, and I'll draw this a little more airfoilish. All right, so it looks kind of like a wing. The airfoil is what applied that force. So if it applies that force this direction on the air is pushing back. The air is pushing back on the airfoil. Initially, this airfoil, and I've exaggerated it greatly, this airfoil is moving in this direction. That's my initial velocity. That's what V sub I is. The applied change is in the direction of the force. That force is pushing it, and so it should be parallel, so that my new velocity then, and these are all vector quantities, my final velocity is in that direction. And that's where I get that lift from. That component of lift comes from the fact that I'm making it move upwards. And it's a result of the fact that I'm swatting at molecules of air, if you will, pushing them downward. They in turn are pushing backwards. Now the thing to remember is that this force is always normal to the direction of travel. It's normal to my surface, actually, sorry. That force is always normal to the surface. And so the more I can get this wing to be downward, if I don't exaggerate it the way I did, then I can actually get it to lift a larger load, because more of that force, if you go back to POE and the physics, vector physics, it's directing it more in a vertical direction. Now there's two important terms that we need to look at with this in terms of deflection lift. One of them, and we've kind of talked about it, is relative wind. And I talked a little bit about this last time, but if I have an airplane drawn here, very well, I did a quite artsy job I'm proud of, even with a propeller on the front. If it's traveling this way, it experiences a wind component that's directly opposite to that in the direction of travel, opposite the direction of travel. If at the same time I had a wind component this way that was the prevailing winds, what we call the prevailing winds, then what I actually get as a result is the relative wind is the vector addition of those two. And it is the result of essentially the wind resistance from the travel of the airplane and the normal wind that if we were sitting still in our airplane at 30,000 feet, which is a scary thought, you would feel blowing on you if you were just sitting still there. And so that's the thing. So we get this relative wind. And back to it, so we need that. We'll deal with that with angle of attack in a moment. And as we go through this in more detail, but that is also, you'll remember why we actually yaw the airplane. We yaw it so that it goes into the relative wind, and we take advantage of that, and it's not being pushed along, because you don't want that wind to push on the side. If that relative wind is blowing this way, it's going to do that, and it's going to have the effect as the aircraft moves this way of pushing it off course. And so you turn it into the relative wind so that you are not constantly correcting your course. You're going straight in the direction that you want to go, even though that direction is this way and your aircraft would be turned this way. All right. The other term that we want to express that's important to us is angle of attack, which I will constantly abbreviate AOA, since it's the only AOA we have in aerospace. Angle of attack is the angle defined between, for now, we'll just kind of deal with it as the chord of the wing, and that's from the first point at which the air hits the wing. Let me just kind of draw a wing here. And so if the wind is this way, if the relative wind is horizontal, if it was nice that way, then it would first hit, let's say, at this point in the tail of the wing. So it's not necessarily the full width of the wing. It kind of depends on how the chord that makes relative, the angle between that, and the relative wind. The angle between those two is the angle of attack. Okay, so that's, if the wind is that direction and the chord is that direction, then that's my angle of attack. My angle of attack is up here. It would be that. So that's going to kind of give us, and that's important, the angle of attack is going to affect that deflection lift. As this bends, that's what I said, I really would like for my airfoil to be more oriented this way, a little more horizontal, so that if I draw this out in vector quantities, there's my normal force, a bigger portion of it is acting upward as opposed to what I did on my one up here, on my example up here. You have a bigger component. Bigger component acting vertically means I have more lift, means I get a bigger weight off of the ground. All right, the last thing that I want to deal with, and then I'm going to leave coanda and circulation lift, and we'll talk about those in class. I have a demo for you. But I want to talk about Bernoulli lift a little bit, and I'll just introduce it. Bernoulli lift, as we talk about this, we said it's you have a tube that I have air flowing through, and then it goes back out again, and this is called a venturi. And if I have air flowing through here, as it approaches this narrowness, it's got to speed up, and it gets kind of squeezed together, but it's got to speed up to get through there, because in the end, I have to have the same amount of air going through this smaller portion and out the other end than I do the same amount as what's coming in here. Otherwise, my pipe would balloon up, and it won't do that. Even though we're not dealing with pipes, we're dealing with an unlimited airspace, the concept is still the same. What happens at this point, and I think I did this before. Yeah, I did. So whatever my velocity, my initial velocity and my initial pressure are right here, as we approach this narrow region, the velocity's got to go up. The velocity's got to go up, and when it does, the pressure goes down, and I'll explain why that is. And then when it goes back to, afterwards, and it goes back to the same shape, in theory anyway, the velocity and pressure return to their normal positions. Now, here's what's happening. Here's what Bernoulli's equation says. Bernoulli's equation says, and by the way, in case you didn't know it, K stands for constant. Bernoulli's equation says that if I take the gravitational potential energy plus the kinetic energy plus the static pressure of the air, and this is where it really works, those have to be a constant value, whatever they are, relative to the operation of our airfoil. They have to be a constant value. What that means, the gravitational potential energy is mgh. The kinetic energy is 1/2 mv squared, and the pressure is just P. And if we look at that and calculate that out, mgh is the same because we're talking about a constant altitude. The only thing then that can change is the velocity and the pressure. So we're dealing with two situations. Let's go with situation 1 here, where we have whatever my velocity and my pressure is, I'm going to call V1 and P1, As the air approaches the airfoil, and I'm probably drawn very poorly, some of it's got to go up and over, and it's going to make trail lines. And the really cool thing, if we can find a way to do it, people who do wind tunnel testing can do this with smoke, for example. But some of this air is going to compress up and over here, and it's going to come out here. Some of it's going to go this way, and it takes a slower path. And so what's happening right in here in area 2, I have V2 and P2. Well, actually, I have two different V2s and P2s. I have V2 below the wing, and I have V2, P2 above the wing. And then eventually everything kind of returns back to normal. So out here far enough away from the wing, everything kind of gets back to, the air goes back to where it was before. The key is what's happening here is Bernoulli's equation. Above the wing, very fast and low pressure. Below the wing, should have done this in a different color. Slower, maybe not very slow. Slower, but higher pressure. Because of Bernoulli's equation. As the velocity slows down, the pressure goes up below the wing. As the velocity speeds up above the wing, the pressure goes down, because that has to be a constant in my entire environment that I'm working with. And so literally we lift an airplane off the ground with nothing more than a difference in pressure above and below the wing, and we're going to create enough of a difference that actually creates a lift that will work, that will do that. And that's Bernoulli lift. And as I said, I will finish up with Coanda and circulation lift in class, and we'll kind of go back over this because I know we might have missed a few things here and there.